Microscopy and morphology of bacteria. Introduction. Bacteria belong to the group of prokaryotes. Difference between the prokaryotes and eukaryotic cells are shown. They are living structures of a microscopic size. They are measured in units of an micrometer. The bacteria of medical importance measures 2 to 5 micrometer into 0.2 to 1.5 micrometer. The resolution power of unaided eye is about 200 micrometer. Hence the study of bacteria requires the use of microscope. A microscope is done for the following purposes: magnification of an object, maximization of the resolution, optimization of the contrast between the structure of organisms and the background. The following types of microscopes are being employed for the study of bacteria: optical and light microscope. The light microscope contains a light source and a compound lens system. The lens system consists of a number of objective lenses in conjunction with a fixed, usually 10x ocular eyepiece lenses. Light microscope are equipped with objective lenses of low power 10x, high power 40x, and oil immersion 100x, which will result in the final magnification in conjugation with ocular lenses of 100x, 400x, 1000x respectively. The visualization of bacteria generally requires the use of immersion oil with 100x objectives. This combination results in resolution of approximately 0.2 micron. However, 40x objective is used for examination of wet preparation, example hanging drop, stool for ova, and face contrast microscope. The face contrast microscope includes the contrast and make evidence and internal structures of the cells which differs in thickness or refractive indexes. The different parts of the cells and its surrounding medium have got different refractive indexes. When rays of light are passed through an object, they emerge in different phases depending on the difference of the refractive indexes between the object and its surrounding medium. The special optical system, a special condenser and objective lenses converts the difference in phases into the difference in intensity of the light, producing light and dark contrast in the image. The light microscope can be converted into the phase contrast microscope by using the special condenser and objective lenses. A dark field microscope, dark ground microscope. The refracted light is used instead of transmitted light used in the light microscope. A dark field condenser with a circular stop is fitted with the light microscope. This condenser lens system is arranged in such a way that no light reaches the eye unless reflected from the object. The object or bacterium appears self-luminous against a dark background. The spirochetes can be seen under a dark field microscope. Fluorescent microscope. The fluorescent is a phenomenon that occurs when an object is impacted by a given wavelength of light and emits light at a wavelength longer than the one to which it is exposed. The fluorescent microscope specimens are exposed to light of shorter wavelength UV light, which results in the emission of longer wavelength visible light. And due to the shorter wavelength of UV light, the resolving power can be appropriately extended. The bacteria stained with the fluorescent, example auramine, becomes visible as a brightly glowing object in a dark background. The fluorescent microscope has also been employed for the detection of antigen and antibody. Electron microscope. Beam of electron is employed instead of a beam of light used in optical microscope. The electron beam is focused by a circular magnetic sensor which are analogous to the lens of light microscope. The wavelength of the electron is approximately 0.005 nanometer as compared to 500 nanometer with visible light. The resolving power of any microscope is directly related to the wavelength. Thus, the resolving power of electron microscope should be theoretically 10,000 times that of light microscope, but in practice it is about 0.1 nanometer. Study of bacteria unstained preparations. The unstained preparations are examined mainly for the bacterial motility, example hanging drop preparations, and for determination of spirochetes, example dark background microscope. Stain preparation. The structural details of bacteria cannot be seen under light microscope due to the lack of contrast. Hence, it is necessary to use stain methods to produce the color contrast. The smear made for bacteria culture or specimen is first dried and then fixed with heat by flaming the slide for underneath. The heat killed and fixes the bacteria on a slide due to the coagulation of bacterial proteins. The fixed smear is stained by a approximately staining technique. Common staining technique: simple stain. The basic stain such as a methylene blue or basic friction is used as a simple stain. They provides the color contrast but imparts the same color to all bacteria in the smear. Negative stain. Bacteria are mixed with the dyes such as Indian ink or nigrosin. The background gets stained and unstained bacteria stand out in the contrast. This is very useful in demonstration of bacterial capsule which do not take simple stain. Impregnation method. Bacterial cells and the structures that are too thick too thin to be seen under light microscope are thickened by impregnation of silver on the surface to make them visible. Example, demonstration of bacterial flagella and spirochetes. Differential staining. They imports different colors of different bacteria or bacterial structures. The two most commonly employed differential stainings are gram staining and acid fast staining. Gram staining is most widely used in bacteriology. The stains are originally devised by histologist Christian Gram. Nowadays, modification of the original gram stain is used. Modification heat fixes smears of the specimen or bacterial culture is stained with a crystal violet primary stain for 1 minute for paraso and dyes such as gentian violet or methyl violet may also be used as a primary stain. Pour grams iodine diluted solution of iodine over a slide for 1 minute. Wash the smear with water. Decolorize with acetone for 10 to 30 minutes. Alcohol can be sustained for acetone. Wash the smear with water. Coat stain with the dye saffron for 30 seconds. Dilute carbon friction or neutral red may also be used as a counter stain. Differential gram staining. Two broad groups, gram positive and gram negative. Gram positive resist decolorization, resist the color of primary stain, that is violet. Gram negative decolorized by acetone alcohol and therefore they counter stain and appears red. Acid fast stain is Zeal stain. The acid fast stain was discussed by Ehrlich and subsequently modified by Zeal and Nielsen staining of mycobacterium. Usually tubercle or leprobacilli is done by this technique method. The carbon friction stain is poured on the slide containing fixed smear. Gently heat is applied to the underside of the slide by means of a spirit flame until the stain just commences to steam. The carbon friction is left on the slide for 5 to 10 minutes with the intermittent heating during that period. The care must be taken to ensure that the stain does not dry out. To counteract drying, more solutions of stain is added to the slide and slide reheated. Heating of the stain is required for penetration of the dye into the cell wall. Wash in tap water. The stained smear is decolorized with 20% of sulfuric acid and wash in with water. This step should be repeated till the pink red color stops coming out. In case of leprobacilli, 5% sulfuric acid is used as a mycobacterium leprae is less acid fast. Another alternative for decolorization is acid alcohol 3 ml of HCl and 97 ml ethanol. The smear is in counterstain with 2% methyl blue for 1 to 2 minutes. Molecular green can also be used as a counterstain of methylene blue. Wash with water and air dry. Microscopic examination of the smear. Acid fast basically appears red. The color of the carbon fission is blue. Color of methyl blue. Background of the pus cells and epithelial cells. Morphology depending on the shape. Bacteria are broadly classified into cocci and bacilli. Cocci are oval or spherical shape. These cocci may be arranged in pairs, diplococci chains, streptococci clusters, staphylococci and groups of 4 tetrad or 8. The bacilli or rod-shaped cells. Some of these bacilli may be having peculiar arrangement or shape such as a cocobacilli, Brucella bacilli in chain. Examples: streptobacilli, Chinese letter or a cuneiform pattern, corynebacterium, comma-shaped. Example: Vibrio or Spiralium. Bacterial anatomy. Bacterial cells consist of a following components: cell wall, cytoplasm or plasma membrane, cytoplasm, cytoplasmic inclusions, mesosomes, ribosomes, inclusion granules and vacuoles. A single cellular chromosomes of deoxyribonucleic acid DNA. Beside these essential components, some bacteria may possess additional structures such as a capsule, flagella, and fimbriae. Cell wall. The cell wall is a tough and rigid structure surrounded the bacteria like a shell. It is 10 to 25 nanometer thick. Its weight about 20 to 25% of dry weight of the cell. The rigid part of the cell wall is peptidoglycan. The cell wall of the gram-positive bacteria have a simpler chemical nature than those of gram-negative bacteria. Functions of cell wall accounts for the shape of the cell, provides protections to the cell against the osmotic damage, confers rigidity upon bacteria. It takes part in the cell division. It possesses a target site for antibiotics, lysosomes, and bacteriophages. It carries bacterial antigens that are important in virulence and immunity. Gram-negative cell wall. This gram-negative cell wall is a complex structure with the following component: lipoprotein layer, outer membrane, lipopolysaccharide. Lipopolysaccharide constitutes the endotoxin of gram-negative bacteria. This layer consists of a lipid A to which it attaches to the polysaccharide. The polysaccharide determines a major surface antigen, the O antigen. The toxicity of the bacteria is associated with the lipid A. the peripheral space, the peptidoglycan, gram-negative, gram-positive cell wall. The following components are present: peptidoglycan. This layer is gram-positive bacteria, and it is thicker than that in gram-negative bacteria. Teichoic acid, gram-positive cell wall contains a significant amount of teichoic acid, which is absent in the gram-negative bacteria. Bacteria with the defective cell wall, say mycoplasma, L forms protoplasm and spiroblast. Cytoplasmic membrane, it acts as a semi-permeable membrane. It also contributes to the enzyme necessary for cell wall synthesis. Cytoplasm, it contains ribosomes, mesosomes, vacuoles, and inclusions. Ribosomes, these are the centers of a protein synthesis. Intracytoplasmic inclusions, these are the source of stored energy and present in some species of bacteria. Examples is Voltron granules in, say, Corynebacterium diphtheria. Mesosomes are a vesicular multinucleated or convoluted structure formed as a invaginations of a plasma membrane into the cytoplasm. They are the principal centers of respiratory enzymes, more prominent in gram-positive bacteria. There are two types of mesosomes, septal and lateral nucleus. The bacterial nucleus has no nuclear membrane or a nucleolus. The genetic DNA is double-stranded in the form of circles. The bacterial DNA maintains a bacterial genetic characteristics. Some bacteria may possess extra nuclear genetic materials in the cytoplasm containing DNA named as a plasmid or episomes. Bacterial capsules under a slime layer. It is amorphous viscid bacterial secretion which is around some bacteria as the outermost layer. When it remains as a loose under marketed secretion, it is known as slime layer. When this secretion is organized into a sharply defined structure, it is known as a capsule. Functions: capsule enhances the bacterial virulence by inhibiting phagocytosis. It acts as a protective covering against antibacterial synthesis. The capsular antigen can be used for the identification of typing of bacteria. Capsulation of organisms: Streptococcus pneumonia, Klebsiella species, Bacillus anthracis, Cryptococcus neoformans, fungi. Demonstration of capsule: Indian ink staining, negative staining. Capsule appears as a clear halo around the bacteria. Quilling phenomena. Special capsule staining. Flagella are cytoplasmic appendages protruding through cell wall. These are composed of proteins 5 to 20 micrometer in length and 0.02 micrometer in diameter. They are organ of locomotion, part of composition. Each flagella consists of three parts: filament, hook, and basal body. Arrangement type: monotrichous, amphitrichous, lophotrichous, and peritrichous. Demonstration: flagella are about 0.02 micrometer in thickness and hence beyond the resolution limit of light microscope. The following methods are used for demonstration: dark ground illumination, special staining technique in which the thickness of the flagella is increased by moderating. Electron microscopy, indirect method, swarming growth of proteins, hanging drop preparations, and Craigie tube method. Fimbriae, these are hair-like appendages projecting from the surface as a straight filaments. They are also called sepali. They are about 0.1 to 1.0 micrometer in length and less than 10 nanometer thick. Fimbriae are found in some gram-negative bacteria. Fimbriae is composed of a protein called pilin. Types: common PD, 6 or F PD, called I PD. Functions: addition, transfer of genetic material by conjugation. Direction of Fimbriae: electron microscopy and hemagglutination. Bacterial spores. The spores are highly resistant to resting stage, formed in unfavorable environmental conditions, presumed to be related to the depletion of exogenous nutrients. As bacterial spores are formed within the parent cells, they are called endospores. Sporulation: bacterial cells undergoes spore formation in nutritionally deprived conditions, and this process is called sporulation. Spore developed from a portion of a protoplasm near one end of the cells. The remaining part is called as a sporangium. Detailed process of sporulation in the table. Morphology of spores: core, spore membrane, spore cortex, spore coat, exosporium. Shapes and position of spores: shapes: oval or spherical. Positions: non-budding spores, central, subterminal, terminal. Bulging spores, central, subterminal, terminal. Resistance: bacterial spores are extremely resistant to ordinary boiling, disinfectant, and heating. The spores of all medically important bacteria are destroyed by autoclaving. Germination: the process of conversion of a spore into vegetative cells under suitable conditions is known as germination. The demonstration: gram staining. Spore appears as unstained refractory bodies within the cell. Modify Zeil-Nielsen staining. Spores appears as acid first red cells. In this method, 0.25 to 0.5% sulfuric acid used as a decolorizing agent. Uses a spore indicator for proper sterilization. Example: spores of Bacillus styrothermophilus. Spore forming bacteria: Bacillus species, Clostridium species.